Tonight, we're going to explore one of the strangest mysteries in our entire solar system. Every planet spins. That's normal. But there's one planet that spins in a way that shouldn't be possible. Uranus is tilted so far on its side that it's practically rolling around the sun like a ball on a track. Its axis is tipped nearly 98 degrees. That means while every other planet spins somewhat upright, like tops on a table, Uranus is lying on its side, pointing its poles almost directly at the sun. Something catastrophic happened to this world. Something violent enough to knock an entire planet over. And the terrifying part is, we're still not completely sure what did it. By the end of tonight, you're going to understand what we think happened, and why the answer changes everything we know about how our solar system was built. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you might not have thought much about. Every planet in our solar system is spinning. Right now, as you listen to this, Earth is rotating on its axis, completing a full turn about once every 24 hours. That rotation is what gives us day and night. When your side of Earth faces the sun, it's daytime. When it rotates away, darkness falls. Simple enough. But Earth isn't spinning perfectly upright. If you imagine a line running from the North Pole to the South Pole straight through the center of the planet, that line is Earth's rotational axis. Now, if Earth's axis were pointing straight up and down relative to its orbit around the sun, we'd have no seasons. Every day would be about the same length. The equator would always get the most direct sunlight, the poles would always be cold, and not much would change throughout the year. But Earth's axis isn't straight up and down. It's tilted. Earth leans at about 23.5 degrees from the vertical. This means that as Earth orbits the sun over the course of a year, different parts of the planet get more or less direct sunlight at different times. When the northern hemisphere is tilted toward the sun, it's summer in the north and winter in the south. 6 months later, the situation reverses. The southern hemisphere tilts sunward, and it's summer down there while the north gets winter. This tilt is why seasons exist. Without it, there would be no summer, no winter, no spring, no fall. The whole climate system of Earth, the migration patterns of animals, the growing seasons of plants, the rhythms of human civilization for thousands of years, all of it traces back to the fact that Earth's axis is tilted 23.5 degrees. That number matters. It's not random. And it's not extreme. 23.5 degrees is a modest lean. Enough to give us noticeable seasons, but not so much that the climate becomes chaotic or unrecognizable. Earth is, in a sense, tilted just right for the kind of world we experience. Now, here's what most people don't think about. And every planet has an axial tilt. Every planet in the solar system has its own lean, its own angle between its rotational axis and the plane of its orbit. And for most planets, this tilt is relatively modest. Mercury is tilted at only about 0.02 of a degree, essentially zero. Mercury spins almost perfectly upright relative to its orbit. This means Mercury has no seasons to speak of. The amount of sunlight hitting any given latitude doesn't change much throughout its year. Venus is tilted about 177 degrees. Now, that sounds extreme, and technically it is, but what it actually means is that Venus is almost upside down. It is tilted so far that it's nearly flipped over, which means it effectively rotates backward compared to most other planets. Venus spins in the opposite direction from Earth. If you could somehow stand on Venus and watch the sun, it would rise in the west and set in the east. But in terms of how much Venus leans relative to the vertical, it's really only about 3 degrees from being completely upside down. So its effective tilt is very small. Venus, like Mercury, has almost no meaningful seasons driven by axial tilt. Mars is tilted at about 25 degrees. That's remarkably close to Earth's tilt. Mars has seasons for the same reason Earth does. Its poles take turns leaning toward and away from the sun. Mars even has polar ice caps that grow and shrink with the seasons, expanding in winter as carbon dioxide freezes out of the thin atmosphere, and retreating in summer as it sublimates back into gas. If you could stand on Mars in the middle of its northern summer, you'd experience something recognizable. Longer days, more direct sunlight, warmer temperatures. Not warm by Earth standards because Mars is much farther from the sun and has a thin atmosphere, but the seasonal pattern would feel familiar. Jupiter, the largest planet in the solar system, is tilted only about 3 degrees. Jupiter is nearly upright. This means Jupiter doesn't really have seasons in any meaningful sense. Its massive atmosphere is driven almost entirely by internal heat, rather than by seasonal variations in sunlight. The bands and storms you see on Jupiter, including the famous Great Red Spot, are powered by processes happening deep inside the planet, not by changes in how sunlight hits it throughout the year. Saturn is tilted about 26.5 degrees, similar to Earth and Mars. Saturn does have seasons, and they're visible. The colours and patterns in Saturn's atmosphere shift subtly as the planet orbits the Sun. Saturn's rings also change their appearance from Earth depending on the season, sometimes appearing edge-on and nearly invisible, sometimes tilted to show their full breadth. A year on Saturn lasts about 29.5 Earth years, so each season lasts more than 7 years. So to summarize what we've seen so far, most planets in the solar system are tilted modestly. A few degrees here, 20-something degrees there. The range is manageable. The tilts produce seasons of varying intensity, but nothing truly extreme. The planets spin more or less upright, like tops on a table, each one leaning a little bit one way or the other, but fundamentally oriented in a way that makes sense given how they formed. And then there's Uranus. Uranus has an axial tilt of about 97.8 degrees. Let that number settle in your mind for a moment. 97.8 degrees. That's not a modest lean. That's not even a dramatic lean. That's a planet lying on its side. If Earth were tilted this much, the North Pole would point almost directly at the Sun for part of the year, and then 6 months later, the South Pole would take its turn. Seasons wouldn't be gentle shifts in temperature and daylight. They would be absolute extremes. One pole baking in continuous sunlight for months, while the other sat in total darkness. The entire climate system of the planet would be radically different from anything we experience. Uranus is the only planet in the solar system with a tilt this extreme. No other planet comes close. Earth is at 23.5 degrees, Mars is at 25, Saturn is at 26.5. These are all in the same range. Even Venus, which is technically tilted at 177 degrees, is effectively spinning nearly upside down with a very small effective tilt from the vertical. Uranus is different. Uranus isn't slightly tilted, dramatically tilted, or even flipped upside down. It's sideways. Imagine a spinning top. Normally, a top spins with its axis pointing up and down. If you pushed it a little, it would lean but keep spinning. If you pushed it a lot, it might tip over and spin flat on the table. That's essentially what Uranus does. It's rotating with its axis nearly in the plane of its orbit, as if someone reached out and shoved it over. To understand why this is so strange, you need to understand how planets form and why we'd expect them to spin in a particular way. Our solar system formed about 4.5 billion years ago from a massive cloud of gas and dust called the solar nebula. This cloud was made mostly of hydrogen and helium, with traces of heavier elements, the remnants of older stars that had exploded and scattered their materials across space. At some point, something disturbed this cloud. Maybe a shock wave from a nearby supernova, maybe random gravitational fluctuations, but something caused a region of the cloud to begin collapsing under its own gravity. As the cloud collapsed, it began to spin. This is a fundamental consequence of something called the conservation of angular momentum. It's the same principle that makes an ice skater spin faster when they pull their arms in. The cloud had a tiny amount of rotation to begin with, and as it contracted, that rotation sped up. The spinning cloud flattened into a disk, like pizza dough being spun in the air. At the center of the disk, the material was densest and hottest. This is where the sun formed. Around the sun, the remaining material in the disk began to clump together. Tiny grains of dust stuck to each other, forming pebbles. Pebbles accumulated into rocks. Rocks grew into boulders. Boulders merged into planetesimals, objects perhaps a kilometer or more across. And planetesimals collided and merged to form protoplanets, the embryos of the planets we know today. This process, called accretion, happened within the flat disk. Everything was orbiting the young sun in roughly the same direction, in roughly the same plane. And because the material in the disk was all moving in the same general direction, the planets that formed from it inherited that motion. They ended up orbiting the sun in the same direction and roughly the same plane. They also ended up spinning in the same direction, rotating on their axes in the same sense as their orbital motion. This is called prograde rotation. Most planets have prograde rotation because they formed from material that was all moving the same way. And here's the key point. Because the planets formed from this orderly disk of material, we'd expect their rotational axes to be roughly perpendicular to the plane of the disk. In other words, we'd expect them to spin more or less upright, with small tilts that might result from the random accumulation of material during formation. Small variations are normal. A planet might end up tilted a few degrees because the last few larger objects that crashed into it during formation happened to hit it at a slight angle. But a tilt of 98 degrees is not a small variation. It's a catastrophic departure from what the physics of planet formation predicts. Something happened to Uranus after it formed, or during the late stages of its formation, that fundamentally altered its orientation. Something hit it, pulled it, or pushed it so violently that it ended up lying on its side. And whatever that something was, it had to be extraordinarily powerful. Because Uranus is not a small object. Not by any stretch. Uranus has a diameter of about 31,518 miles. That makes it about 4 times wider than Earth. If you placed Earth next to Uranus, Earth would look like a marble next to a basketball. But size only tells part of the story. Uranus has a mass of about 14.5 times Earth's mass. That's an enormous amount of material. Roughly 8.681 times 10 to the 25th kilograms. To tilt something that massive to change the orientation of its entire rotational axis by nearly 98 degrees requires a staggering amount of energy. It's not like pushing a ball on a table, it's like pushing over a mountain. Whatever happened to Uranus had to deliver enough force to overcome the rotational inertia of a planet 4 times wider than Earth and nearly 15 times as massive. Uranus orbits the Sun at an average distance of about 1.8 billion miles, roughly 19 times farther from the Sun than Earth is. At that distance, the Sun appears as a small bright dot in the sky, about 1/370th as bright as it appears from Earth. Uranus takes about 84 Earth years to complete a single orbit. A year on Uranus is 84 Earth years long. If you were born on Uranus, you'd celebrate your first birthday at the age of 84 by Earth standards. Almost no human who has ever lived has experienced a full Uranian year. William Herschel, who discovered Uranus in 1781, never saw it complete even half an orbit after its discovery. It wouldn't return to the same position in the sky where Herschel first spotted it until 1865, long after his death. Uranus is classified as an ice giant, a term that can be a little misleading. When astronomers say ice giant, they don't mean the planet is covered in frozen water like an enormous snowball. They mean that a large fraction of the planet's mass is made up of heavier volatile compounds. Things like water, ammonia, and methane, in addition to the hydrogen and helium that dominate the atmospheres of the larger gas giants like Jupiter and Saturn. These compounds exist under such extreme pressures and temperatures deep inside Uranus that they behave in strange ways. Water might exist as a superheated fluid, a state where it's neither liquid nor gas, but something in between. At even deeper levels, some scientists believe the pressures could be great enough to create exotic states of matter. Possibly even a rain of diamonds formed when carbon atoms in methane are squeezed together under immense pressure. The methane in Uranus's upper atmosphere is actually responsible for the planet's distinctive blue-green color. Methane absorbs red wavelengths of sunlight and reflects blue and green wavelengths back into space. That's why Uranus appears as a pale blue-green disk when viewed through a telescope. It's a beautiful color, serene and calm looking, but that calm appearance is deceiving. Something deeply violent happened to this world. Uranus also has a system of 13 known rings. These rings are much fainter and narrower than Saturn's spectacular ring system. They were discovered in 1977 when astronomers were observing Uranus pass in front of a distant star. Before the planet blocked the star's light, the star dimmed several times as the rings passed in front of it. This was unexpected. At the time, Saturn was the only planet known to have rings. The discovery of rings around Uranus showed that ring systems might be more common than previously thought. Neptune was later found to have faint rings as well. Beyond the rings, Uranus has 27 known moons. These moons are named after characters from the works of William Shakespeare and Alexander Pope. The 5 largest are Miranda, Ariel, Umbriel, Titania, and Oberon. Titania is the largest, with a diameter of about 981 miles. That's less than half the diameter of Earth's moon. These moons are small, icy worlds, each with its own unique features. Miranda, the smallest of the 5 major moons, is particularly strange. Its surface is one of the most chaotic and fractured landscapes in the entire solar system. a jumbled patchwork of wildly different terrains pressed together in ways that seem almost random. Some regions are ancient and heavily cratered, while others look young and geologically reworked, carved with deep grooves and ridges that suggest powerful forces were at work, reshaping the moon from the inside out. No other moon in the solar system looks quite like Miranda. It appears to be a world that was torn apart or violently disrupted and never fully recovered. A world that wears its traumatic history on its face. We'll come back to Miranda because its scarred surface may hold some of the most important clues to whatever catastrophic event reshaped the entire Uranian system. For now, it's enough to know that Miranda looks like something terrible happened to it, and so does its parent planet. Here's something crucial about the moons and rings of Uranus that deepens the mystery. They don't orbit in the plane of the solar system. They orbit in the plane of Uranus's equator. This means the moons and rings are tilted along with the planet. They're sideways too. The entire Uranian system, planet, rings and moons, is tipped over together. This tells us something important. Whatever tilted Uranus likely happened early, before the current moon system formed in its present configuration, or the moons were somehow dragged along during the tilting process. If Uranus had been tilted recently, say a few 100 million years ago, we'd expect the moons to still be orbiting in the original plane, not the tilted one. The fact that they orbit in the equatorial plane suggests the tilt happened long ago and the moon system had time to settle into the new orientation, or that the moons formed from debris generated during the event that caused the tilt in the first place. And this is where a comparison to Neptune makes the mystery even more striking. Because if there's one planet in the solar system that should be similar to Uranus, it's Neptune. The two planets are nearly the same size. Neptune's diameter is about 30,599 miles, only slightly smaller than Uranus. Their masses are comparable. Neptune is about 17 times Earth's mass. Uranus, about 14.5. They're both ice giants, composed of similar mixtures of hydrogen, helium, water, ammonia, and methane. They both orbit in the cold outer reaches of the solar system, far from the sun's warmth. They formed from the same protoplanetary disk, built from the same raw materials, shaped by the same physical forces. If any two planets in the solar system should look and behave alike, it's these two. And yet, when it comes to axial tilt, they couldn't be more different. Neptune is tilted at about 28 degrees. That's almost identical to Earth's tilt. It's modest, unremarkable, exactly what you'd expect from a planet that formed normally from the solar nebula. Neptune spins upright, with gentle seasons that play out over the course of its 165-year orbit. There's nothing strange about Neptune's orientation. It follows the rules. Uranus, its near twin, is tilted 98 degrees. That's a difference of 70 degrees between two planets that should be almost identical. 70 degrees separating a planet that behaves normally from a planet that rolls on its side. Whatever happened to Uranus didn't happen to Neptune. Whatever force was powerful enough to tip over a planet 14.5 times Earth's mass somehow spared Neptune, a planet of similar size orbiting in the same region of the solar system. This makes the mystery sharper. It's not just that Uranus is tilted, it's that its near twin is not tilted. The question isn't just what happened to Uranus, it's why did it happen to Uranus and not to Neptune? These two planets started out as siblings, built from the same materials in the same part of the solar system. Today, one spins normally, and the other lies on its side. Something separated their fates. Something intervened in one planet's history and left the other untouched. And that something must have been specific to Uranus. Not a general process that affected all the outer planets equally, but a targeted event or a particular set of circumstances that singled out Uranus and left it fundamentally altered while its sibling remained intact. So what we're looking at is a planet that defies expectation. A world that should be spinning more or less upright, like its neighbours, but instead lies on its side. A world whose entire system of moons and rings has been tipped along with it. A world that formed in an orderly disk of gas and dust, where everything was rotating in the same direction, and yet somehow ended up with its axis pointed almost directly along its orbital path. A world whose nearest twin, a planet of almost identical size and composition, spins normally while Uranus alone was knocked sideways. Everything about Uranus's orientation screams that something went wrong. Something broke the rules. The neat and tidy story of planets forming from a disk and inheriting orderly spins doesn't work for Uranus. Something intervened. Something powerful enough to tip over a planet 14.5 times the mass of Earth. The question is, what? And this is where the story gets really interesting. Because scientists have been wrestling with this question for decades. The tilt of Uranus has been a known puzzle since at least the early 20th century, when astronomers first measured it with enough precision to realize just how extreme it was. And over the years, several explanations have been proposed. Some involve unimaginable violence. Collisions so powerful they reshaped an entire world. Others involve subtler forces, slow gravitational nudges that accumulated over millions of years, gradually pushing the planet further and further from its original orientation until it toppled over. Each explanation has its strengths, each has its weaknesses, and none of them has been definitively proven beyond doubt. The truth is, we're still not sure what tipped Uranus on its side. We have leading hypotheses. We have computer simulations that can reproduce the tilt under certain conditions. We have physical evidence from the planet itself, its magnetic field, its moons, its rings, its atmosphere that provides clues. But we don't have a definitive answer, not yet. What we do know is this. The tilt of Uranus is not a minor curiosity. It's not just an interesting trivia fact about the seventh planet. It's a window into the history of the solar system itself. Because whatever happened to Uranus didn't happen in isolation. It happened in the context of a young solar system that was far more violent, far more chaotic, and far more dangerous than the orderly place we see today. The solar system we live in now, with its neatly spaced planets following nearly circular orbits, is the end result of billions of years of evolution. But the early solar system was nothing like this. It was a war zone. Protoplanets smashing into each other. Giant planets migrating inward and outward, reshaping the entire architecture of the system. Debris raining down on everything. Entire worlds being destroyed, ejected from the solar system entirely, or fundamentally altered by the violence around them. Uranus carries the scars of that era. Its sideways spin is a record of some things that happened billions of years ago, preserved in the orientation of the planet itself. And understanding what caused that tilt means understanding what the early solar system was really like. That's the journey we're going to take. We're going to look at the leading ideas. We're going to examine the evidence. We're going to explore what simulations tell us and where they fall short. And we're going to see how the tilt of Uranus doesn't just affect the planet's orientation. It shapes its seasons, its magnetic field, its weather, and the orbits of its moons in ways that are unlike anything else in the solar system. But it all starts with the simple observation that something is deeply wrong with how Uranus spins. Every other planet follows the rules. Uranus broke them. And figuring out why is one of the most compelling detective stories in all of planetary science. To understand what might have happened to Uranus, you first need to understand what the solar system looked like when Uranus was young. Because the solar system you see today, with planets following neat, nearly circular orbits, spaced out in an orderly arrangement, is not what the solar system looked like 4.5 billion years ago. Not even close. The early solar system was chaos, absolute chaos. And if you could somehow travel back in time and witness it, you would barely recognize it as the same system we live in today. After the sun ignited at the center of the collapsing solar nebula, the leftover gas and dust settled into a rotating disk. Within that disk, the process of building planets began. We've already talked about how small particles clump together into progressively larger objects. But what we haven't talked about is just how crowded and violent that process was. Because the disk didn't contain just a handful of growing objects. It contained billions of them. Planetesimals ranging from 1 kilometer across to hundreds of kilometers across filled the space around the young sun, all orbiting at different speeds, all on slightly different paths, and all crashing into each other constantly. This was the era of accretion, the era when planets were being built, piece by piece, collision by collision. And it was violent beyond description. Imagine a demolition derby, except instead of cars, the participants are objects the size of mountains and small moons, and instead of a dirt track, the arena is hundreds of millions of miles wide. Objects were colliding at speeds of several kilometers per second. Some collisions were gentle enough that the objects stuck together, growing larger. Others were so energetic that both objects were shattered, reduced to rubble that would eventually reassemble or be absorbed by other growing bodies. The larger an object became, the stronger its gravitational pull, and the more material it attracted. This created a runaway effect. The biggest objects grew the fastest because their gravity swept up more and more debris. These growing bodies are called protoplanets, and within the first 10 to 20 million years after the solar nebula formed, several protoplanets had grown large enough to dominate their regions of the disk. These would eventually become the planets we know. But here's the thing. There weren't just 8 protoplanets. There were probably dozens, maybe more. Computer simulations of planet formation consistently show that the early solar system likely contained many more planet-sized bodies than the 8 we have today. Some of these bodies were in unstable orbits. Their gravitational interactions with one another sent them careening through the solar system on wild, eccentric paths. Some were flung outward into the cold reaches beyond Neptune. Some were hurled inward, where they either crashed into the sun or were ejected from the solar system entirely, sent spinning off into interstellar space to wander the galaxy forever as rogue planets. And some of them crashed into other protoplanets. These weren't small impacts. These were collisions between objects the size of planets. Entire worlds slamming into each other at velocities measured in tens of kilometers per second. The energy released in such events is almost beyond calculation. A collision between 2 planet-sized bodies can release energy equivalent to the sun's entire output over several weeks, all concentrated into just a few violent hours. The impact generates temperatures of tens of thousands of degrees. Both objects can be partially or completely melted. Enormous quantities of debris are blasted into orbit around the impact site, forming temporary disks of molten rock and vaporized material that can eventually cool and coalesce into moons. We actually have strong evidence that this kind of catastrophic collision happened to Earth itself. The leading theory for the formation of our moon is the giant impact hypothesis. About 4.5 billion years ago, a Mars-sized body called Theia is believed to have struck the young Earth at an oblique angle. The collision was so violent that it melted a significant portion of Earth's mantle and blasted an enormous amount of debris into orbit. That debris eventually coalesced to form the moon. This hypothesis explains many things about the Earth-Moon system. It explains why the moon has a relatively small iron core, because the impactor's iron core merged with Earth's core during the collision, while the debris that formed the moon was mostly mantle material. It explains why the isotopic composition of moon rocks is very similar to Earth's mantle, and it explains why the Earth-Moon system has as much angular momentum as it does. Mercury provides another example. Mercury has an unusually large iron core relative to its size. About 85% of Mercury's radius is taken up by its core. One explanation is that early in Mercury's history, a massive impact stripped away most of the planet's outer rocky layers, leaving behind mostly the dense iron core. The collision essentially peeled Mercury, removing its crust and much of its mantle, and leaving behind the dense metallic interior. Venus rotates backward compared to most planets, spinning clockwise instead of counterclockwise when viewed from above the North Pole. One possible explanation is that a giant impact early in Venus's history either flipped the planet upside down or slowed its rotation so much that tidal interactions with the Sun eventually reversed it. The point is this: giant impacts were not rare events in the early solar system. They were normal. They were part of the planet-building process. Almost every major body in the solar system shows evidence of having been shaped, in one way or another, by catastrophic collisions. And if a Mars-sized impact could create Earth's moon, if an impact could strip Mercury of its mantle, if a collision could alter Venus's rotation, then it's entirely plausible that an impact could have knocked Uranus on its side. This is the leading hypothesis for Uranus's extreme tilt. At some point during the late stages of planet formation, roughly 4 to 4.5 billion years ago, a massive body slammed into Uranus with enough force to tip the planet over. The impactor would have been enormous. Simulations suggest it needed to be somewhere between 1 and 3 times the mass of Earth. That's not a small asteroid or comet. That's a full-size planet. An object thousands of miles across, with its own gravity, its own internal structure, possibly even its own atmosphere. And it hit Uranus at a speed of several kilometers per second. Let's think about what that collision might have looked like, because the scale of it is genuinely difficult to grasp. Uranus, already a massive planet, perhaps not yet at its full current size but close to it, is orbiting the young Sun in the outer reaches of the solar system. The impactor, a rocky or icy body roughly the size of Earth or larger, is on an intersecting orbit. Maybe it was a protoplanet that had been gravitationally scattered by Jupiter or Saturn, flung outward into the region where Uranus was forming. Maybe it was a body that had formed nearby and whose orbit had gradually become unstable. Whatever its origin, it's on a collision course. As the two bodies approach each other, their mutual gravity accelerates them toward one another. The closing speed increases. In the final hours before impact, the impactor would be visible from Uranus as a rapidly growing disk in the sky, swelling from a point of light to a world-sized object in a matter of hours, and then impact. The collision is not like anything in human experience. There's no explosion in the conventional sense, no fireball mushrooming upward because there's no atmosphere to speak of in the way we understand it. Instead, there's a titanic transfer of a kinetic energy. The impactor slams into Uranus at an angle. At the point of contact, pressures spike to millions of times atmospheric pressure on Earth. Temperatures at the impact site soar to tens of thousands of degrees. Both the impactor and the region of Uranus it strikes are instantly heated beyond anything found on the surface of the Sun. A shock wave ripples through the interior of Uranus, propagating at speeds of kilometers per second, compressing and heating everything it passes through. Material is blasted outward from the impact site. A plume of superheated gas, vaporized rock, and molten ice erupts from the collision point, sending debris arcing into space. Some of this debris escapes Uranus's gravity entirely and goes into orbit around the Sun. Some of it falls back onto the planet, and some of it goes into orbit around Uranus, forming a temporary disk of debris that glows white-hot against the blackness of space. But the most important effect of the collision is the transfer of angular momentum. The impactor doesn't just deliver energy, it delivers a push. And because the impact is oblique, hitting at an angle rather than head-on, that push has a rotational component. It applies a torque to Uranus, twisting the planet's spin axis. If the impact is large enough and hits at the right angle, this torque can change the orientation of the entire planet. It can tip Uranus over. This is exactly what computer simulations show. The first detailed simulations of a giant impact on Uranus were published in the early 1990s by Wayne Slattery, Willie Benz, and Alistair Cameron. They used what are called smoothed particle hydrodynamic simulations, a technique that models the planet and the impactor as collections of thousands of individual particles, each one representing a chunk of matter. The simulation tracks how each particle moves, how it interacts with its neighbors, how pressure and temperature change during the collision, and how the overall system evolves over time. What Slattery and his colleagues found was striking. A single impact from an object roughly 1 to 2 Earth masses, hitting Uranus at a glancing angle, could reproduce the planet's current tilt of roughly 98 degrees. The simulations showed the impactor plunging into Uranus, delivering its angular momentum and fundamentally altering the planet's spin. After the impact, the simulated Uranus was lying on its side, rotating with its axis nearly in the plane of its orbit, just like the real Uranus. These early simulations were groundbreaking because they demonstrated that a single, physically plausible event could explain one of the most puzzling features of our solar system. You didn't need exotic physics. You didn't need mysterious unknown forces. You just needed a big rock hitting a big planet at the right angle. And given what we know about the violence of the early solar system, such a collision was entirely reasonable, but there was a problem. Actually, there were several problems. While the single impact model could reproduce the tilt, it struggled with some of the details. One major issue was temperature. The simulations showed that a single giant impact would deliver so much energy that it would heat Uranus's interior enormously. The planet would be left with a hot, well-mixed interior. But observations of Uranus suggest something different. Uranus radiates very little internal heat compared to the other giant planets. Neptune, which is similar in size and composition, radiates about 2.5 times more energy than it receives from the Sun. This excess energy comes from heat left over from Neptune's formation and from the slow gravitational contraction of the planet's interior. Uranus, by contrast, radiates almost no excess heat. It gives off roughly the same amount of energy it receives from the Sun. This suggests that Uranus's interior might not be as hot as we'd expect, or that something is preventing heat from escaping. A single massive impact should have deposited a tremendous amount of heat into the planet. So why is Uranus so cold inside? Some researchers suggested that the impact might have disrupted the normal convection patterns inside Uranus. In most giant planets, heat is transported from the interior to the surface by convection, the same process that causes hot air to rise and cold air to sink. If the impact created layers of different composition inside Uranus, layers that don't mix easily because of differences in density, then convection could be suppressed. Heat would be trapped deep inside the planet, unable to reach the surface. This could explain why Uranus appears cold on the outside, while potentially harboring significant internal heat. Another problem with the single impact model involved Uranus's moons. As we discussed, Uranus's major moons orbit in the planet's equatorial plane. They're tilted along with the planet. If a single giant impact tilted Uranus, what happened to any moons that existed before the impact? They should have been left behind in their original orbital plane, not dragged along to the new tilted equator. One possibility is that the pre-existing moons were destroyed or ejected during the impact, and the current moons formed later from the debris disk created by the collision. This is plausible. We think Earth's moon formed from the debris of the giant impact with Theia. A similar process could have happened at Uranus. The impact blasted enough material into orbit to form a debris disk, and the moons gradually coalesced from that disk in the new equatorial plane. But the details are tricky. Simulations have had difficulty producing a debris disk from a single impact that's massive enough and has the right properties to form all of Uranus's known moons. Some simulations produce too little debris. Others produce debris with the wrong composition. The moons of Uranus are made largely of ice and rock, and getting the right mix of materials in the debris disk requires the impact to occur under specific conditions, specific impact angle, specific impactor composition, specific velocity. It's possible, but requires fine-tuning. This led some scientists to propose an alternative version of the impact hypothesis. Instead of one giant impact, maybe Uranus was tilted by 2 or more smaller impacts. This idea has some attractive features. Multiple impacts, each one tipping the planet a little further, could build up to the current 98-degree tilt without any single event needing to be as catastrophic as the one impact scenario requires. Each individual impact would deliver less energy, which means less heating of the interior. This could help explain why Uranus radiates so little internal heat. If the planet was tilted gradually through several smaller impacts, rather than one enormous one, the total energy deposited might have been distributed over a longer period, allowing the planet to cool between events. Multiple impacts also avoid some of the fine-tuning problems of the single impact model. Instead of requiring one impactor to hit at exactly the right angle, with exactly the right mass at exactly the right speed, you allow for several impactors, each contributing some fraction of the total tilt. The probability of 2 or 3 Earth mass impacts over the course of 100 million years is arguably more realistic than one single perfect collision. However, the multiple impact scenario has its own challenges. The biggest is statistical. Each additional impact you require makes the overall scenario less probable. One giant impact on Uranus during the era of planet formation is plausible. 2 giant impacts are less likely. 3 are even less likely. At some point, you're stacking up so many coincidences that the scenario becomes improbable. Also, multiple impacts from random directions would tend to cancel each other out. One impact might tilt the planet 20 degrees to the left. The next might tilt it 30 degrees to the right. The net effect could be smaller than any individual impact. To build up a coherent 98-degree tilt from multiple impacts, they'd need to predominantly push in the same general direction, which requires some degree of coincidence. More recent simulations, published in the 2010s and 2020s, have explored both scenarios in greater detail using more powerful computers and more sophisticated models. These newer simulations can track millions of individual particles rather than thousands, allowing for much higher resolution. They can model the interiors of Uranus and the impactor in greater detail, including different layers of composition, hydrogen and helium envelopes, icy mantles, and rocky cores. Some of these newer studies have found that a single oblique impact from an object about 1 to 3 times Earth's mass can reproduce not only the tilt, but also several other features of the Uranian system. The impact can create a debris disk from which moons could form. It can produce internal layering that suppresses convection and explains the low heat flux. It can even affect the planet's magnetic field, which, as we'll explore later, is one of the strangest magnetic fields in the solar system. One particularly influential study published in 2018 by Jacob Kegaris and colleagues at Durham University in England used high-resolution simulations to model a range of impact scenarios. They found that a grazing impact, one where the impactor hits at a shallow angle and doesn't penetrate deeply into Uranus's interior, could tilt the planet to its current orientation, while leaving much of the deeper interior relatively undisturbed. This is important because it means the impact could change the planet's spin without necessarily delivering enormous amounts of heat to the core. The impactor would deposit most of its energy in the outer layers of Uranus, heating and disrupting the envelope, while leaving the deeper interior cooler. This could help explain both the tilt and the lack of internal heat radiation. The Kegaris simulations also showed that the impact could confine the debris to a thin region close to the planet, creating conditions favorable for moon formation in the equatorial plane. Different impact angles and velocities produced different outcomes. Some produced large amounts of debris, enough to form several moons. Others produced less debris but achieved the correct tilt. The researchers found a range of plausible scenarios, not just one specific impact, that could explain what we see at Uranus today. But what happened to the impactor itself? This is a question that doesn't get asked often enough. If an Earth-sized body slammed into Uranus, where did it go? In most simulations, the impactor doesn't survive as a separate object. It's either completely absorbed into Uranus, its material mixing with the planet's existing mass, or it's shattered and partially absorbed, with some debris escaping into orbit or into space. If the impactor was rocky, its material would have sunk toward Uranus's center, adding mass to whatever solid core the planet already had. If the impactor had a significant ice component, that material might have mixed with Uranus's icy mantle. In either case, the impactor's identity as a separate body would have been erased. It became part of Uranus. There's no separate object to find. The evidence of the impactor's existence is written into Uranus itself, into its tilt, its internal structure, its magnetic field, and possibly its moons. This raises an interesting point about the composition of Uranus. Uranus and Neptune are often grouped together as ice giants, similar in size and bulk composition, but there are differences between them that might be explained by the impact. Uranus radiates less internal heat than Neptune. Uranus has a more extreme axial tilt. Uranus's magnetic field is more offset and tilted relative to its rotation axis than Neptune's. These differences could all be consequences of the giant impact that Uranus experienced, and Neptune didn't. The two planets may have started out more similar than they are today, with the impact transforming Uranus into the oddball we observe. It's also worth noting that the giant impact hypothesis for Uranus fits neatly into a broader understanding of the early solar system's history. Planetary scientists have long known that the early solar system underwent a period of dramatic upheaval. The leading model for this upheaval is called the Nice model, named after the city of Nice in France where it was developed. The Nice model proposes that the giant planets, Jupiter, Saturn, Uranus, and Neptune, did not form in the orbits they occupy today. Instead, they formed in a more compact configuration, closer together and closer to the Sun. At some point, about 500 to 700 million years after the planets formed, gravitational interactions between Jupiter and Saturn triggered a cascade of instability. Jupiter migrated slightly inward. Saturn, Uranus, and Neptune were pushed outward. This migration was not smooth. It was violent and chaotic. The orbits of Uranus and Neptune may have actually crossed at one point, with the two planets swapping positions. The migration scattered billions of icy planetesimals from the outer disk, sending some into the inner solar system, where they bombarded the rocky planets. This is believed to be the cause of the late heavy bombardment, a period of intense cratering that we see evidence of on the Moon, Mercury, and Mars. During this period of migration and instability, the conditions were perfect for giant impacts. Protoplanets that hadn't been fully incorporated into the main planets were still floating around in the outer solar system. The gravitational chaos caused by the migrating giant planets could have sent these leftover bodies onto collision courses with the planets themselves. Some models even suggest there may have been a fifth giant planet in the early solar system, a world similar to Uranus or Neptune that was gravitationally ejected into interstellar space during the instability. If such a planet existed, it could have interacted with Uranus before being ejected, possibly even being the impactor that knocked Uranus over. This is speculative, but it illustrates how the giant impact on Uranus fits into the larger story of solar system evolution. It's not an isolated event. It's part of a pattern of violence and upheaval that shaped every planet in the solar system. The evidence supporting the giant impact hypothesis is strong, though not conclusive. It's the simplest explanation that accounts for the most observations. It explains the tilt. It's consistent with what we know about the violent early solar system. It's supported by computer simulations that can reproduce the tilt under realistic conditions. And similar impacts are known to have shaped other worlds in our solar system. The formation of Earth's moon, the stripping of Mercury's mantle, the possible reversal of Venus's rotation, all of these point to a solar system where giant impacts were common and consequential. But the giant impact hypothesis is not the only idea on the table. There are alternative explanations that don't require a collision at all. These alternatives are more speculative, and they face their own challenges. But they're worth exploring because science works by considering multiple possibilities and testing them against the evidence. The impact hypothesis is the leading idea, the one most planetary scientists would point to if pressed for an answer. But it hasn't been proven beyond doubt. There are still open questions, still features of the Uranian system that the impact model struggles to fully explain. And until we can resolve those questions, possibly with data from a future spacecraft mission to Uranus, the door remains open to other explanations. What those alternative explanations look like, and why some scientists think the answer might be more subtle than a single catastrophic collision, is where this story takes its next turn. Because sometimes in science, the most obvious answer isn't the complete answer. Sometimes the truth is stranger than a planet-sized rock smashing into a world and knocking it sideways. Sometimes the real mechanism is quieter, slower, and in many ways, even more remarkable. The giant impact hypothesis is elegant. It's dramatic. It fits neatly into what we know about the violent early solar system. And for most planetary scientists, it remains the leading explanation for why Uranus is tilted on its side. But science doesn't work by simply accepting the most popular idea and moving on. Science works by poking holes in explanations, by asking what doesn't fit, by looking for the details that the leading theory struggles to explain. And when you look closely at the giant impact hypothesis, there are details that don't quite work. Not enough to overthrow the idea entirely, but enough to make some researchers wonder if the full story might be more complicated. Enough to inspire alternative explanations that approach the problem from entirely different angles. These alternatives are more speculative than the impact hypothesis. They don't have the same weight of evidence behind them, but they're worth understanding because they reveal just how much we still don't know about Uranus, and because some of them are genuinely fascinating in their own right. Let's start with the problems. The issues that have made some scientists uncomfortable with the simple one impact story. The first and most persistent problem is the moons. Uranus has 27 known moons, and the 5 largest, Miranda, Ariel, Umbriel, Titania, and Oberon, all orbit in the planet's equatorial plane. They're tilted along with the planet. Their orbits are nearly circular. They're prograde, meaning they orbit in the same direction Uranus rotates. And they appear to have formed from a circumplanetary disk, a disk of gas and debris that surrounded Uranus after it formed, similar to the disk that gave rise to the large moons of Jupiter and Saturn. Now, if a giant impact tilted Uranus, you'd expect it to also create debris that could form moons. And indeed, simulations show that a giant impact can produce a debris disk. But here's the issue. In many simulations, the debris disk produced by the impact doesn't have the right properties to form the moons we actually see. The total mass of Uranus's 5 major moons is relatively small, only about 1/10,000th of Uranus's total mass. That's not a lot of material. A giant impact from an Earth mass or larger impactor would typically produce far more debris than is needed. Where did the excess go? Some of it might have fallen back onto Uranus. Some might have been ejected from the system. But getting the balance just right, producing enough debris to form the moons, but not so much that you form moons far more massive than the ones we observe, requires specific conditions. The impact has to hit at a particular angle with a particular velocity and a particular mass ratio. This fine-tuning isn't impossible, but it makes some scientists uneasy. There's another issue with the moons. If the impact destroyed any pre-existing moons and the current moons formed from impact debris, then the moons should be made primarily of material from the impact itself, a mixture of Uranus's outer layers and the impactor's material. But we don't know the detailed composition of Uranus's moons well enough to test this. We've only had one spacecraft visit the Uranian system, Voyager 2, which flew past in January 1986. Voyager 2 gave us our only close-up images of the planet and its moons. It revealed incredible details. Miranda's bizarre patchwork surface, the fractured terrains of Ariel, the dark ancient surface of Umbriel. But Voyager 2 was a flyby mission. It spent only a few hours in the Uranian system before continuing on to Neptune. It couldn't orbit the planet, couldn't study the moons in detail, couldn't measure their compositions with the precision we'd need to test the impact hypothesis. We simply don't have enough data. There's a second problem that goes beyond the moons. It has to do with the spin rate of Uranus. An impact powerful enough to tilt Uranus 98 degrees would also change the planet's rotation speed. Depending on the angle and velocity of the impact, it could speed up or slow down Uranus's spin. The current rotation period of Uranus is about 17 hours and 14 minutes. That's a specific number, and any successful impact model needs to reproduce it. Some simulations do reproduce it. Others produce a Uranus that spins too fast or too slowly. Getting both the tilt and the spin rate right simultaneously adds another constraint to the model, another parameter that needs to be tuned. And there's a third issue, one that's more subtle, but potentially very important. It has to do with the obliquity itself, the angle of the tilt. 98 degrees is very close to 90 degrees. It's almost but not quite a perfect right angle. If Uranus had been tilted by exactly 90 degrees, its pole would point exactly along its orbital path. But it's tilted slightly past 90 degrees by about 8 degrees. This means Uranus technically has a retrograde rotation. It spins in the opposite direction from what you'd expect if you defined its north pole the same way you define Earth's north pole. This slight overshoot past 90 degrees might be significant. A single impact might naturally produce a tilt near 90 degrees, but the specific value of 98 degrees might carry information about the tilting mechanism. Was it one impact that overshot? Two impacts that didn't quite cancel out? Or a different process entirely? These problems don't disprove the giant impact hypothesis. They're not fatal flaws, but they've motivated some researchers to explore alternative mechanisms. Mechanisms that could tilt Uranus without any impact at all. The most prominent alternative involves something called a spin-orbit resonance. To understand this, you need to know a little bit about how resonances work in orbital mechanics. A resonance occurs when two orbiting bodies exert regular, periodic gravitational influences on each other, because their orbital periods are related by a simple ratio. For example, if one body orbits a central object once for every 2 orbits of another body, they're in a 2-to-1 resonance. Every time they line up, they give each other a small gravitational tug in the same direction. Over time, these small tugs add up and can produce large effects. Resonances are common in the solar system. Pluto is in a 2-to-3 resonance with Neptune, completing 2 orbits for every 3 of Neptune's. Several of Jupiter's moons are in resonances with each other. Io, Europa, and Ganymede are in a 1-2-4 resonance. Every time Ganymede completes one orbit, Europa completes 2, and Io completes 4. These resonances lock the moons into a precise orbital dance, and are responsible for the tidal heating that makes Io the most volcanically active body in the solar system. Now, a spin-orbit resonance is similar in concept, but involves the spin of a planet rather than the orbit of a moon. Specifically, it's a resonance between the rate at which a planet's spin axis precesses, that is, wobbles in a circle like a tilted spinning top, and the rate at which the planet's orbit changes orientation. If these two rates match, the planet can get locked into a resonance that gradually increases its axial tilt over time. Here's how it could work for Uranus. Early in the solar system's history, the giant planets were interacting gravitationally with a massive disk of leftover planetesimals. This disk exerted gravitational torques on the planets, causing their orbits to precess, to slowly change orientation over millions of years. At the same time, each planet's spin axis was also precessing at its own rate, determined by the planet's shape, spin speed, and the gravitational influence of the Sun and other planets. If Uranus's spin axis precession rate happened to match the precession rate of its orbit, the two motions could become locked together in a resonance. When this happens, the gravitational interactions don't cancel out over time. Instead, they accumulate. Each small tug pushes the spin axis a little further from vertical. Over millions of years, these small pushes could build up, tilting Uranus further and further, eventually reaching the extreme tilt we see today. This is an attractive idea for several reasons. First, it doesn't require a catastrophic impact. The tilting happens gradually over millions of years, through the slow accumulation of gravitational effects. This means there's no sudden injection of enormous energy into the planet's interior. Uranus could be tilted without being significantly heated, which would naturally explain why the planet radiates so little internal heat. Second, it's a deterministic process rather than a chance event. Resonances arise naturally from the gravitational interactions between planets and the disk. You don't need to invoke a specific impactor hitting at a specific angle with a specific velocity. The tilting is a consequence of the system's orbital architecture. However, the spin-orbit resonance hypothesis has significant challenges of its own. The biggest challenge is making the resonance work quantitatively. For the resonance to capture Uranus and tilt it all the way to 98 degrees, very specific conditions need to be met. The disk of planetesimals needs to have the right mass. The precession rates need to match closely enough for the resonance to engage. And the resonance needs to be maintained long enough, millions of years, for the tilt to build up to its current value. Several research groups have studied this mechanism in detail. Some have found that spin-orbit resonances can indeed produce large tilts under certain conditions, but getting all the way to 98 degrees is difficult. In many models, the resonance produces tilts of 40 or 50 degrees before the conditions change and the resonance breaks. The disk dissipates, the orbital architecture shifts, and the tilting stops before reaching the extreme values we observe. Getting to 98 degrees typically requires very specific assumptions about the mass and lifetime of the planetesimal disk. There's another version of the spin-orbit resonance idea that involves not a disk of planetesimals, but another planet. Some researchers have proposed that the early solar system contained an additional giant planet. a fifth ice giant similar in size to Uranus or Neptune that was eventually ejected from the solar system during the period of orbital instability described by the NICE model. Before this planet was ejected, its gravitational influence could have driven a spin-orbit resonance with Uranus. As the extraplanet migrated through the outer solar system, its orbital precession rate could have swept through a resonance with Uranus's spin-axis precession rate, capturing it and tilting the planet. When the extraplanet was finally ejected, the resonance would have broken, leaving Uranus tilted at whatever angle it had reached. This scenario is intriguing because there are independent reasons to believe a fifth giant planet might have existed. The NICE model works better with 5 giant planets than 4. A fifth planet provides additional gravitational interactions that help explain the current orbital architecture of the outer solar system, the distribution of objects in the Kuiper belt, and the orbital properties of certain trans-Neptunian objects. If this planet existed and interacted with Uranus before being ejected, it could have tilted Uranus without any collision. But this hypothesis is built on a chain of assumptions. We assume a fifth planet existed. We assume it was in the right orbital configuration to drive a resonance with Uranus. We assume the resonance was maintained long enough to produce a 98-degree tilt. And we assume the planet was ejected at the right time. Each assumption is individually plausible, but stacking them together makes the scenario progressively more speculative. There's yet another alternative that involves a massive ancient moon. This idea was proposed more recently and is perhaps the most creative of the alternative hypotheses. The concept goes like this. Early in its history, Uranus had a large moon, much larger than any of its current moons. This moon might have been comparable in mass to Earth's moon, or even larger. As this moon orbited Uranus, tidal interactions between the moon and the planet would have caused the moon to slowly migrate outward, similar to how Earth's moon is currently receding from Earth at a rate of about 1.5 inches per year. As the moon moved outward, its orbital precession rate changed. At some point, the moon's orbital precession rate could have matched Uranus's spin-axis precession rate, creating a resonance. This resonance could have tilted Uranus gradually, just like the spin-orbit resonance described earlier, but driven by the moon rather than by an external planet or disk. The advantage of this mechanism is that the moon is part of the Uranian system itself. You don't need to invoke external bodies or specific disk properties. The tilting mechanism is internal, driven by interactions between the planet and its own satellite. But what happened to this hypothetical massive moon? If it tilted Uranus, where is it now? The answer, according to proponents of this idea, is that the moon was eventually destabilized. As the tilt increased, the gravitational dynamics of the system became increasingly complex. At high obliquities, the moon's orbit can become chaotic. The moon might have been ejected from the system entirely, flung into a heliocentric orbit, and eventually lost. Or it might have collided with Uranus, crashing into the planet and being absorbed. Or it might have been disrupted by tidal forces, broken apart into debris that eventually formed the ring system and perhaps some of the smaller moons we see today. A study published in 2022 by Melaine Seilenfest and colleagues at the Paris Observatory explored this idea in detail. They showed that a moon with a mass of about 1,000th of Uranus's mass, roughly comparable to Earth's moon, could drive Uranus's obliquity from a small initial value all the way to 98 degrees over the course of the solar system's history if the moon migrated outward at a rate consistent with tidal models. The moon would eventually reach a critical distance where its orbit became unstable, leading to its loss from the system. This result was significant because it showed that Uranus's tilt could potentially be explained without any impact at all. The tilting would be gradual, driven by the slow outward migration of a moon. The moon would do the work over billions of years, quietly tilting the planet through a resonance mechanism and then conveniently disappearing when the tilt reached its current value. But this hypothesis faces its own set of challenges. The first is the obvious one. We have no direct evidence that this massive moon ever existed. It's entirely hypothetical. If it was destroyed or ejected, we'd need to find evidence of its former existence, perhaps in the orbital properties of the remaining moons or in the composition of the rings. But we don't have detailed enough data to test this. Again, the lack of a dedicated mission to Uranus limits what we can conclude. The second challenge involves the timescale. In some versions of this model, the tilting happens over billions of years, not just during the early solar system, but continuing well into the solar system's middle age. This is different from the impact hypothesis, which places the tilting event firmly in the first few 100 million years. The timing matters because it affects predictions about the current state of the Uranian system. If the tilting was recent in geological terms, it might have left detectable signatures that a future mission could identify. The third challenge is that even if a massive moon could tilt Uranus, it's not clear why this would happen at Uranus and not at the other giant planets. Jupiter, Saturn, and Neptune all have large moons that could potentially drive resonances. Why didn't they get tilted too? The answer might lie in the specific properties of each planet's moon system, the masses and orbital distances of the moons, the internal structure of the planets, the tidal dissipation rates. But working out these details requires precise modeling, and the results are sensitive to assumptions about parameters we don't know well. There's one more alternative worth mentioning, though it's less developed than the others. Some researchers have suggested that Uranus's tilt could be primordial, that it could have arisen during the planet's formation rather than from a later event. In this view, the angular momentum of the material that formed Uranus was oriented differently from the material that formed the other giant planets. Perhaps Uranus formed in a region of the protoplanetary disk where local turbulence or gravitational interactions with nearby protoplanets created unusual flows of gas and dust. The planet might have accreted material with angular momentum vectors pointing in different directions, and the net result was a spin axis tilted far from the expected vertical. This idea is the least popular of the alternatives because it's difficult to reconcile with our understanding of how protoplanetary disks work. The disk is generally well ordered, with material flowing in the same direction. Large deviations from this orderly flow are possible but uncommon, and producing a tilt as extreme as 98 degrees purely through accretion seems to require very special conditions. Most planetary scientists consider this explanation unlikely, though it hasn't been rigorously ruled out. So where does all this leave us? We have a leading hypothesis, the giant impact, that explains the tilt and is consistent with the violent early solar system. But it struggles with some details, particularly the properties of the moon system and the low internal heat flux. We have alternative hypotheses, spin orbit resonances, a lost massive moon, primordial formation effects that address some of these details but introduce their own assumptions and challenges. The honest answer is that we don't know for certain what tilted Uranus. This might be surprising. We've sent spacecraft to every planet in the solar system. We've mapped the surfaces of moons. We've landed on comets. We've driven rovers across Mars. You might think we'd have solved a basic question like why a planet is tilted. But Uranus is one of the least studied planets in the solar system. Voyager 2's flyby in 1986 remains our only close encounter. That was nearly 4 decades ago. The spacecraft was built with the 1970s technology. It carried instruments that were state-of-the-art for their time, but are primitive by today's standards. It spent only a few hours in the Uranian system before flying on to Neptune. Since then, we've studied Uranus from Earth and from Earth orbit using telescopes like Hubble and the James Webb Space Telescope. These observations have revealed new details about the planet's atmosphere, its rings, and its moons. But telescopic observations from nearly 2 billion miles away can only tell us so much. To truly understand what happened to Uranus, to distinguish between the competing hypotheses, we need to go back. We need a dedicated mission. In 2022, the United States National Academies of Sciences published its Planetary Science and Astrobiology Decadal Survey, a document that sets priorities for planetary exploration over the next decade. The survey identified a Uranus orbiter and probe as the highest priority flagship mission for the coming years. This mission, if funded and built, would send a spacecraft to orbit Uranus for several years, studying the planet's interior structure, magnetic field, atmosphere, rings, and moons in unprecedented detail. It would also drop a probe into Uranus's atmosphere, measuring its composition and structure as it descended through the clouds. Such a mission could provide the data needed to distinguish between the competing explanations for Uranus's tilt. Detailed measurements of the moon's compositions could reveal whether they formed from impact debris or from a circumplanetary disk that predated any impact. Precise mapping of the magnetic field could tell us about the internal structure and whether it bears the signature of a giant impact. Measurements of atmospheric composition and thermal structure could constrain models of the planet's evolution and help determine how much internal heat is trapped beneath the surface. But a mission to Uranus would take time. The planet is nearly 2 billion miles away. Even with a gravity assist from Jupiter, a spacecraft would take about 13 years to reach it. Add several years of development and construction, and we're looking at results no sooner than the late 2030s or early 2040s at the earliest. And that's assuming the mission gets funded, which in the world of space exploration is never a certainty. Until then, we're left with models, simulations, and the limited data we already have. And we're left with a profound question that doesn't have a definitive answer yet. What happened to Uranus? Was it a single catastrophic collision that knocked it over in a matter of hours? Was it 2 or more smaller collisions that progressively tilted it over millions of years? Was it a slow gravitational resonance driven by a now vanished disk of debris or a now ejected planet? Was it a massive ancient moon that quietly tilted its parent planet over billions of years before being swallowed or lost? The truth might be some combination of these. Maybe an impact did most of the work, but a resonance finished it off. Maybe a massive moon existed and was later destroyed by the same impact that contributed to the tilt. The real history of Uranus might be more complex than any single model captures. The solar system is 4.5 billion years old. A lot can happen in 4.5 billion years. And Uranus, sitting in the cold outer reaches of the solar system, far from the sun, far from our spacecraft, far from our easy reach, has been keeping its secrets for a very long time. What we do know is that the tilt is real, and whatever caused it, the consequences have been profound, because a 98-degree lean doesn't just change a number in a textbook. It changes everything about how a planet works. It reshapes the physics of an entire world in ways that are visible, measurable, and in some cases deeply strange. The cause of the tilt remains an open question, but the effects of that tilt have been playing out for billions of years, written into every feature of Uranus, from its atmosphere to its magnetic field to the orbits of its moons. And those effects reveal a planet unlike anything else in the solar system. Whatever knocked Uranus on its side, whatever combination of violence and gravity and time produced that 98-degree tilt, the result is a planet unlike anything else in the solar system. Because the tilt doesn't just sit there as an abstract number, it reaches into every aspect of how Uranus behaves. It shapes the planet's seasons. It warps its magnetic field. It determines how sunlight hits its atmosphere and drives its weather. It dictates the orientation of its rings and the orbits of its moons. Uranus is not just a tilted planet. It's a planet whose entire existence has been reorganized by that tilt. And understanding how the tilt manifests in the planet's behavior tells us not only about Uranus itself, but about how planetary systems work in general. Let's start with seasons, because this is where the tilt produces its most dramatic and immediately understandable effects. On Earth, seasons happen because the planet's 23.5-degree tilt causes different hemispheres to receive more or less direct sunlight at different times of the year. In summer, your hemisphere is tilted toward the sun. Days are longer. Sunlight hits at a more direct angle, delivering more energy per square meter. In winter, your hemisphere tilts away. Days are shorter. Sunlight arrives at a shallower angle, spreading its energy over a larger area. The result is a familiar cycle of warm and cold, growth and dormancy that repeats every year. Now, imagine the same process, but with a tilt of 98 degrees. On Uranus, the poles don't just lean toward the sun, they point almost directly at it. During the Uranian summer solstice, the planet's south pole is aimed nearly straight at the sun. The entire southern hemisphere is bathed in continuous sunlight. Not just long days, continuous, unbroken daylight for years. Meanwhile, the northern hemisphere is plunged into complete darkness. Not just long nights, total darkness for years on end. No sunrise, no sunset, just an unrelenting absence of light. And this isn't a brief seasonal event. Uranus takes about 84 Earth years to orbit the Sun. Each season lasts roughly 21 Earth years. That means the South Pole spends about 21 years in continuous sunlight, followed by about 21 years of continuous darkness. The North Pole experiences the reverse. For more than 2 decades at a stretch, one pole bakes in perpetual daylight, while the other sits in perpetual night. There is no human equivalent to this. Nothing on Earth even comes close. Our longest polar days and nights last about 6 months, and even then, the sun never gets very high above the horizon at the poles. On Uranus, the pole that's facing the sun has the sun nearly directly overhead, pouring energy into that hemisphere with an intensity that, while much weaker than what Earth receives due to Uranus's enormous distance from the sun, is still highly concentrated on one region of the planet. Between the solstices come the equinoxes, twice during each 84-year orbit. Uranus reaches a point where neither pole is pointed at the sun. The sun shines on the equator, and the entire planet experiences something resembling a normal day-night cycle, with the sun rising and setting every 17 hours as Uranus rotates. These equinoxes are brief compared to the long solstice seasons, but they're important because they represent a dramatic shift in how energy is distributed across the planet. The atmosphere, which has spent decades adjusting to sunlight concentrated on one pole, suddenly has to readjust to sunlight arriving at the equator. Uranus last passed through an equinox in 2007. This was the first equinox observed with modern telescopes and instruments. And it revealed something surprising. As the sun crossed Uranus's equator, the planet's atmosphere became noticeably more active. Storms appeared, cloud features brightened, banding patterns in the atmosphere shifted. Uranus, which had long been considered one of the blandest and most featureless planets in the solar system, turned out to have weather after all. It just needed the right seasonal trigger to show it. This leads to one of the genuinely puzzling aspects of Uranus. Given the extreme seasonal forcing, the decades-long periods where one hemisphere is heated while the other freezes, you might expect Uranus to have the most violent and dynamic atmosphere in the solar system. You might expect enormous storms driven by the temperature contrast between the sunlit and dark hemispheres. You might expect powerful winds and dramatic weather patterns. But for much of the time we've observed Uranus, the planet has appeared remarkably calm. When Voyager 2 flew past in 1986, it was near the southern solstice. The South Pole was pointed almost directly at the sun, and the planet appeared almost completely featureless. A smooth, pale blue-green sphere with almost no visible cloud features, no bands, no storms, nothing like the turbulent atmospheres of Jupiter and Saturn. This was deeply puzzling. Why would a planet with such extreme seasonal variations have such a bland atmosphere? Part of the answer is distance. Uranus is about 19 times farther from the sun than Earth. At that distance, the sunlight is roughly 370 times weaker than at Earth. Even with one pole pointed directly at the sun for 21 years, the total energy being delivered is modest. The temperature differences between the sunlit and dark hemispheres are much smaller than you might expect because the sunlight is just so weak. Uranus's atmosphere is cold. Temperatures at the cloud tops hover around minus 357 degrees Fahrenheit. At these temperatures, atmospheric processes happen slowly. The energy available to drive storms and winds is limited. But distance isn't the whole explanation. Neptune, which is even farther from the Sun, at about 30 times Earth's distance, has a much more active atmosphere than Uranus. Neptune has some of the fastest winds in the solar system, reaching speeds of over 1,200 miles per hour. Neptune also radiates about 2.5 times more energy than it receives from the Sun, driven by internal heat left over from its formation. This internal heat powers convection and drives atmospheric circulation, even though Neptune receives very little sunlight. Uranus, by contrast, radiates almost no internal heat. As we discussed earlier, this might be because a giant impact disrupted the planet's interior, creating compositional layers that suppress convection and trap heat deep inside. If the interior heat can't reach the surface, the atmosphere is left to be driven almost entirely by the feeble sunlight, which at 19 astronomical units from the Sun just isn't enough to produce dramatic weather most of the time. However, observations over the past 2 decades have changed the picture somewhat. As Uranus approached and passed through its 2007 equinox, ground-based telescopes and the Hubble Space Telescope detected numerous cloud features and storm systems. Bright methane clouds appeared at various latitudes. Some storms were large enough to cast shadows on the deeper cloud layers below. Wind speeds were measured at several hundred miles per hour in some regions. The atmosphere was far more dynamic than Voyager 2 had seen during its brief flyby. This suggests that Uranus's atmosphere is strongly seasonal. During the solstices, when one pole is in continuous sunlight and the other in continuous darkness, the atmosphere might settle into a relatively stable state. But during the equinoxes, when the distribution of sunlight is changing rapidly, the atmosphere is stirred up. The transition from pole-dominated heating to equator-dominated heating drives circulation changes that produce visible weather. The planet breathes with its seasons, coming alive during the transitions and quieting down during the long solstice periods. Now let's turn to what is perhaps the strangest consequence of Uranus's tilt: its magnetic field. Every planet with a liquid or partially liquid conducting interior generates a magnetic field through a process called a dynamo. Earth's magnetic field is generated by convection currents in its liquid iron outer core. Jupiter and Saturn have magnetic fields generated by convection in their metallic hydrogen interiors. The magnetic fields of most planets share a common characteristic. They're roughly aligned with the planet's rotational axis. Earth's magnetic poles are close to its geographic poles. Jupiter's magnetic field is tilted only about 10 degrees from its rotational axis. Saturn's magnetic field is almost perfectly aligned with its rotation. Uranus's magnetic field is nothing like this. It's tilted about 59 degrees from the planet's rotational axis. That means the magnetic poles are nowhere near the geographic poles. If you had a compass on Uranus, it wouldn't point anywhere near the rotational pole. It would point off at a steep angle, toward a region closer to the equator than the pole. But the tilt is only part of the strangeness. The magnetic field is also offset from the center of the planet. The center of the magnetic field is displaced from Uranus's geometric center by about 1/3 of the planet's radius. This means the field is lopsided. It's stronger on one side of the planet than the other. The magnetic field lines are asymmetric, bulging out more in some directions and compressed in others. The result is a magnetosphere, the region of space controlled by the planet's magnetic field that is unlike anything else in the solar system. Most planets have magnetospheres that are roughly symmetric, extending outward from both magnetic poles in a recognizable pattern. Uranus's magnetosphere is twisted and distorted. As the planet rotates every 17 hours, the tilted, offset magnetic field sweeps through space like a wobbly, off-center beacon. The magnetosphere corkscrews behind the planet, creating a long, twisted magnetic tail that trails through the solar wind. This tail writhes and contorts as the planet rotates, changing shape with every spin. Why is Uranus's magnetic field so unusual? This is another open question, and the answer might be connected to whatever caused the tilt. The magnetic fields of planets are generated in their interiors, in regions where electrically conducting fluids are in motion. For Uranus, the dynamo is thought to operate not in a metallic core like Earth's, but in a shell of electrically conducting fluid. likely a mixture of water, ammonia, and methane under extreme pressure that exists in the planet's mantle rather than its core. This is called a shell dynamo, and it naturally produces a magnetic field that's less organized, more tilted, and more offset than a core-centered dynamo would produce. But why does Uranus have a shell dynamo instead of a core dynamo? One possibility is that the giant impact disrupted Uranus's interior structure. A massive collision could have mixed the planet's interior layers, disrupted the original core, or created compositional gradients that changed where and how the dynamo operates. If the impact stirred up the boundary between the core and the mantle, or if it created a stable layer of different composition that prevents convection from reaching the core, then the dynamo would be confined to a shell in the mantle rather than extending to the center. This would naturally produce the tilted, offset magnetic field we observe. Interestingly, Neptune's magnetic field is also tilted and offset, though not as extremely as Uranus's. Neptune's magnetic axis is tilted about 47 degrees from its rotational axis, and the field center is offset by about 55% of the planet's radius. This suggests that shell dynamos might be a common feature of ice giants, a consequence of their internal structure rather than a specific impact event. But the fact that Uranus's field is more extreme than Neptune's could indicate that the impact made things worse, pushing an already unusual magnetic field configuration to an even more extreme state. The magnetic field has practical consequences for the planet. On Earth, the magnetic field creates a protective shield, the magnetosphere, that deflects the solar wind and protects the atmosphere from being stripped away. It also channels energetic particles toward the poles, creating auroras. Uranus has auroras too, but because of the tilted, offset magnetic field, they don't appear at the geographic poles like Earth's auroras do. Instead, they appear at odd latitudes, shifting and distorting as the planet rotates. Observations by the Hubble Space Telescope have detected faint auroral emissions on Uranus, confirming that the magnetic field interacts with the solar wind. But the geometry of this interaction is far more complex than at any other planet. The rings and moons of Uranus also bear the imprint of the tilt. As we discussed earlier, Uranus's 13 known rings and 27 known moons orbit in the planet's equatorial plane. Because the equatorial plane is tilted 98 degrees relative to the orbital plane, the rings and moons are essentially orbiting sideways compared to the rest of the solar system. When seen from Earth, the ring system sometimes appears face-on, a series of concentric circles around the planet, and sometimes appears edge-on, reduced to thin lines barely visible even with powerful telescopes. This changing perspective happens over the course of Uranus's 84-year orbit, as different aspects of the tilted system are presented to our line of sight. The moon's orbits in the tilted equatorial plane create an interesting dynamic. During the solstices, when one pole is pointed at the sun, the moon's orbits carry them in loops that go over and under the sunlit pole. If you could watch from above the sunlit pole, you'd see the moons tracing out roughly circular paths around the planet, passing through both the sunlit and dark hemispheres. During the equinoxes, when the sun is over the equator, the moon's orbits are seen more edge-on, and the moons appear to bob up and down as they circle the planet. The fact that the moon's orbit in the equatorial plane is itself significant, as we've discussed. It tells us that whatever tilted Uranus either happened early enough for the moons to settle into the new equatorial plane, or that the moons formed from debris generated during the tilting event. This is one of the key constraints that any successful theory of the tilt must satisfy. The moons are there, orbiting in the tilted plane, and any explanation for the tilt must account for them. Miranda, the smallest of the 5 major moons, deserves special mention because its surface might carry direct evidence of the violence that shaped the Uranian system. Miranda's surface is a patchwork of terrains that look completely different from one another. There are regions of old, heavily cratered terrain sitting adjacent to regions of young, geologically active-looking terrain with grooves, ridges, and enormous cliffs. The cliffs of Verona Rupes on Miranda are about 12 miles high, the tallest known cliff face in the solar system. If you stood at the top and dropped a rock, it would take about 10 minutes to hit the bottom in Miranda's weak gravity. One explanation for Miranda's bizarre surface is that the moon was shattered by a massive impact, and then slowly reassembled under its own gravity, its fragments coming together in a jumbled arrangement. Another explanation is that Miranda experienced internal geological activity driven by tidal heating, similar to what happens to Jupiter's moon Io. But the activity was incomplete, producing patches of resurfaced terrain amid older cratered regions. Either way, Miranda looks like a world that has been through significant trauma, and that trauma might be connected to the same event or events that tilted Uranus. Now let's zoom out from the specifics of Uranus and think about what this tilted planet tells us about the solar system as a whole. Because the story of Uranus's tilt isn't just about one planet, it's about the nature of planetary systems and the processes that shape them. The solar system we see today looks orderly. 8 planets following nearly circular orbits in roughly the same plane, all orbiting in the same direction, all spinning in the same direction with minor variations. It looks like a well-designed machine, everything in its place, everything running smoothly. But that appearance is deceiving. The solar system we see today is the end result of billions of years of violent evolution. Planets migrated, orbits crossed, protoplanets collided and were destroyed. Entire worlds were ejected into interstellar space. The neat, orderly system we observe is what survived. It's the aftermath of chaos, not the product of calm construction. Uranus's tilt is a reminder of that violent history. It's a scar, a visible, measurable record of something that went catastrophically wrong during the planet's early life. And Uranus isn't alone. As we discussed, Earth's moon was likely formed by a giant impact. Mercury's oversized core suggests another giant impact stripped its mantle. Venus's retrograde rotation might be the result of yet another impact or a combination of impacts and tidal evolution. Mars has a hemispheric dichotomy, a dramatic difference between its smooth northern lowlands and its heavily cratered southern highlands, that some scientists attribute to an enormous ancient impact. Nearly every planet in the solar system carries evidence of having been shaped by violence. This has implications for how we think about other planetary systems. We've now discovered thousands of exoplanets, planets orbiting other stars, and we found that planetary systems come in an enormous variety of configurations. Some have hot Jupiters, gas giants orbiting incredibly close to their stars. Some have super Earths, rocky planets larger than Earth but smaller than Neptune, packed tightly together. Some have planets on highly eccentric orbits that take them swooping close to their star, and then far out into the cold. The diversity is stunning, and much of it can be explained by the same kinds of processes that shaped our solar system. Migration, resonances, gravitational interactions, and giant impacts. If giant impacts can tilt a planet in our solar system, they can do the same in other systems. Some exoplanets might have axial tilts even more extreme than Uranus's. Some might have been tilted by impacts and then had their tilts modified by later gravitational interactions. The axial tilt of a planet affects its climate, its seasons, and potentially its habitability. A planet with an extreme tilt would have extreme seasons. A planet with a no tilt would have no seasons. Both scenarios have implications for the possibility of life. Think about what it would mean for a world in the habitable zone of its star, a rocky planet with liquid water and an atmosphere, to be tilted like Uranus. Imagine a world where one hemisphere faces its star continuously for decades, while the other is plunged into unbroken darkness. On such a world, the sunlit hemisphere would heat relentlessly, ice would melt, oceans would warm, evaporation would intensify, pumping moisture into the atmosphere. Meanwhile, the dark hemisphere would freeze, temperatures would plummet, whatever oceans existed on that side would develop thick ice caps stretching from the pole toward the equator. The atmospheric circulation between the warm and cold hemispheres would be extreme. Powerful winds would howl across the terminator, the boundary between light and dark, driven by the enormous temperature gradient. Storms of a scale and ferocity unknown on Earth would churn through the atmosphere. Then, after decades, the seasons would shift. The previously dark hemisphere would slowly turn toward the star. Ice that had accumulated for a generation would begin to melt. The previously sunlit hemisphere would turn away, plunging into darkness and cold. The entire climate system would reverse. Every ecosystem, if ecosystems existed, would have to cope with transitions between extremes that no life on Earth has ever experienced. Could life survive this? Maybe. Life on Earth has proven extraordinarily resilient. Organisms thrive in boiling hot springs, in the crushing depths of the ocean, in Antarctic ice, in the driest deserts. But the challenge on a Uranus-tilted world wouldn't just be extreme conditions. It would be the constant cycling between opposite extremes, each lasting decades. Life would need to either migrate with the seasons, traveling across hemispheres to follow the sunlight, or enter dormancy for decades at a time, surviving the long dark winter in some kind of suspended state. Or it might adapt to thrive in the twilight zone near the equator, where conditions during the equinox periods are most moderate. The evolutionary pressures on such a world would be profoundly different from anything on Earth. Life that evolved there, if it evolved at all, would be unlike anything we've ever imagined. We can't yet measure the axial tilts of most exoplanets. Our current techniques for detecting and studying exoplanets, transit observations, radial velocity measurements, direct imaging, are better at measuring orbital properties than rotational ones. But as our telescopes and techniques improve, we'll begin to constrain the tilts of at least some exoplanets. And when we do, Uranus will serve as our best case study for understanding what extreme tilt does to a world. Everything we learn about Uranus's seasons, its atmospheric dynamics, its magnetic field, its climate, all of it will inform our understanding of tilted worlds orbiting other stars. Uranus isn't just a curiosity in our own solar system. It's a template for understanding a whole category of worlds we haven't even discovered yet. Understanding what happened to Uranus helps us understand the range of possible outcomes for planetary systems everywhere. It teaches us that planet formation is not a gentle, deterministic process that produces the same result every time. It's a violent, chaotic process full of randomness and contingency. Small differences in the initial conditions, the exact configuration of protoplanets, the timing of gravitational interactions, the angles and velocities of collisions can lead to vastly different outcomes. One planetary system might end up orderly and calm, another might end up with planets tilted on their sides, spinning backward or flung out into the void entirely. And this brings us to the future, because the story of Uranus's tilt is far from over. We've learned an enormous amount from Voyager 2's brief flyby, from decades of telescopic observations, and from increasingly sophisticated computer simulations. But we're still working with limited data. We still don't know the detailed composition of Uranus's moons. We still don't fully understand the planet's internal structure. We still can't definitively distinguish between the competing hypotheses for the tilt. The proposed Uranus orbiter and probe mission, if it's built and launched, would transform our understanding. An orbiter studying the planet for several years could map the magnetic field in detail, revealing the internal structure and the dynamo that generates the field. It could study the moons up close, measuring their compositions and surface features with modern instruments far more capable than anything Voyager 2 carried. It could monitor the atmosphere through seasonal changes, watching how the weather evolves as the planet moves through its 84-year orbit. And a probe descending through the atmosphere could measure the composition of the gases directly, determining the abundances of hydrogen, helium, methane, ammonia, and other compounds that hold clues to the planet's formation and evolution. Such a mission would not just answer questions about Uranus, it would answer questions about ice giants in general. Uranus and Neptune are the least understood class of planet in our solar system, and yet they may represent the most common type of planet in the galaxy. Surveys of exoplanets have found that planets in the size range between Earth and Neptune are extremely common around other stars. Understanding our own ice giants is essential for understanding these distant worlds, but even without a dedicated mission, the mystery of Uranus's tilt continues to inspire research. New simulations are being run, new theoretical models are being developed. Each year, our understanding becomes a little more refined, a little more nuanced. The question of what tilted Uranus has been open for decades, and it might remain open for decades more. But that's how science works. Some questions take a long time to answer. Some answers require new data that we don't yet have the technology to collect. And some mysteries, the deepest and most fascinating ones, resist easy resolution because the truth is more complex than any simple story can capture. What we can say with confidence is this: Uranus's 98-degree tilt is one of the most striking features of our solar system. It tells us that the solar system's history was violent, that giant impacts or other dramatic processes reshaped planets in fundamental ways. It produces consequences that reach into every aspect of the planet's behavior, from its extreme seasons to its twisted magnetic field, to the sideways orbits of its moons and rings. And it stands as a reminder that the orderly solar system we see today was forged in chaos. The calm is an illusion. The scars are everywhere. And on Uranus, the biggest scar of all is written into the very angle at which the planet spins. There's something deeply human about our fascination with Uranus's tilt. We are a species that notices when things are out of place. We walk into a room and sense when a picture is hanging crooked. We feel unsettled when something doesn't match the pattern. And Uranus is the crooked picture in the solar system's gallery. 7 planets, spinning more or less upright, following the rules laid down by the physics of their formation, and one planet lying on its side, defying expectation, demanding an explanation. That dissonance is what drives science. Not just the desire to know what something is, but the need to understand why it doesn't fit, why the pattern breaks, why one case out of 8 is different. Every great scientific discovery begins with someone noticing something that doesn't make sense and refusing to look away. And what makes the Uranus story so compelling is that after decades of research, after thousands of hours of computer simulation time, after the most sophisticated models planetary scientists can build, we still don't have a definitive answer. We have strong candidates. The giant impact hypothesis remains the leading explanation, supported by simulations that can reproduce the tilt under realistic conditions. But the details resist easy resolution. The moons, the internal heat, the magnetic field, the precise angle of 98 degrees rather than 90 or 100. Each detail adds a constraint, narrows the possibilities, and yet the full picture remains just out of reach. This is what makes planetary science, and science in general, so remarkable. We can send spacecraft to other worlds. We can build telescopes that see billions of light years into the past. We can simulate the collision of planets on supercomputers. And yet, a basic question about a planet in our own solar system, why does it spin on its side, remains open. Not because we haven't tried to answer it, but because the universe is complex. Because 4.5 billion years of history leaves ambiguous evidence. Because the truth about what happened to Uranus is locked inside the planet itself, in its internal structure, in the composition of its moons, in the geometry of its magnetic field, waiting for us to develop the tools and build the missions that can finally extract it. The next time you look up at the night sky, you probably won't be able to see Uranus. It's too faint for the naked eye under most conditions, barely visible even under perfect skies, as a dim point of light indistinguishable from a faint star. But it's there. A pale blue-green world rolling on its side nearly 2 billion miles from the sun. A planet that formed from the same disk of gas and dust as Earth, in the same solar system, under the same physical laws, and yet ended up so fundamentally different from our world that it might as well belong to an alien star. Something happened to it. Something enormous. And the evidence of that event is preserved in every feature of the planet, waiting for us to hear it. Waiting for a spacecraft to arrive and finally tell us the full story. And maybe that's the most beautiful part of this story. Not the answer, because we don't fully have it yet, but the question itself. The fact that a planet can roll on its side for billions of years, keeping it secret, and that somewhere on a tiny world orbiting an ordinary star, a species evolved that noticed something was wrong, measured the angle, built the models, ran the simulations, and refuses to stop asking why. The universe doesn't owe us its secrets. It doesn't arrange itself for our convenience or understanding. But we ask anyway. We look at a sideways planet and we want to know. That wanting, that relentless curiosity, that refusal to accept the unexplained, is what brought us from stone tools to spacecraft. It's what will eventually take us back to Uranus. And when we get there, when a spacecraft finally orbits that pale blue-green world and maps its magnetic field and studies its moons and peers into its atmosphere, we'll be one step closer to understanding not just what happened to one planet, but how planetary systems work, how violence and chance and gravity conspire to build the worlds we see, and what our own solar system looked like in its wild, chaotic youth. Until then, Uranus keeps rolling, sideways through the darkness, carrying its secrets. A world that broke the rules and never looked back.